It is a great pleasure for me to introduce the speaker of this talk, Dr. Narayan N, who is going to talk to us about probabilistic methods in graph theory. Dr. Narayan took his PhD degree from Indian Institute of Mathematical Sciences, Chennai, and postdoctoral degree from National Taiwan University. He joined as assistant professor at Indian Institute of Technology, Chennai, in the year 2012. He has published more than 30 papers. His current research interests include graph theory, combinatorics, and graph ideas. On behalf of the Institute and all present here, I now invite Dr. Narayan N to deliver a talk on probabilistic methods in graph theory. Sir, please.
How does this work? I don't send here from the audio. From here? Okay. Okay, so thank you, Ramkumar, for this introduction. And in fact, he should have introduced that like we studied together at university for masters. Yeah, I'm happy to come back here. I think I came several years before once. So today I'm going to talk about what is called probabilistic method, which is a quite powerful tool that has been introduced by Paul Erdős. So Erdős. Then problem with audio? Okay. Okay, better. Okay, so today I'm going to talk about probabilistic method. This idea was introduced by Paul Erdős in the 1940s. So the idea behind probabilistic method is that we want to show the existence of certain combinatorial structures, but we don't know how to probably construct them or how to even verify that whether it is there by direct verification. So in such situations, Erdős suggested that we can actually show the existence using the help of probability. So the idea behind this is very simple. So let us look at this case that you are given x to be the average of, let's say, some n numbers a1 to a. So if x is the average of the n numbers, what can you say about AIs? One thing that you can immediately say is that at least one of these AIs must be greater than or equal to x, right? Without knowing what are the AIs, we can say that at least one of the AIs must be greater than or equal to x, right? So we know immediately that at least one of the AIs must be greater than or equal to x. Similarly, one can say that at least one of the AIs must be less than or equal to X, or can be equal to X. But this is something that we can conclude without knowing anything about AI, right? We only know that what is the average. So the same idea, if you carry over to probability theory, right? Suppose you can show that the probability of certain combinatorial object existing is strictly positive, right? It's greater than 0. Suppose you show somehow that the probability that this exists is greater than 0. You don't know how to find it, but you still show that there is a positive probability. Then Reduce realize that one can conclude that this must exist, right? At least some object of this type must exist. Because if no object of this type exists, then we won't be able to show positive probability. We can only show that probability is greater than 0. To show it strictly greater than 0, that is only if one of the objects of this type exists. Otherwise, it is not possible. Right? So this is the idea behind probabilistic method. So the idea is somehow you show that there is a positive probability for something. So we are going to look at 3 examples, increasing in maybe complexity. But we will start with the first example of Paul, which is constructing a lower bound, finding a lower bound for what are called Ramsey numbers. So what is Ramsey number? Suppose you are looking at the following scenario, right? You are in a bus stop and you meet, let's say, 6 people. You find there's a set of 6 people standing in the bus stop waiting for the bus. Now, in this case, let us assume that 2 people are friends or acquaintances if they have met each other before, and they are strangers if they have not. Now, if you have at least 6 people in the bus stop, then the claim is that there will be at least 3 people who are mutual friends, right? Or 3 people who are mutual strangers, right? Any 2 of them know each other, or any 2 of them who does not know. At least 3 of them must be of this, right? One of this side, right? Either 3 friends or 3 strangers must be there, right? So how do you show that? And if there is 5, we can actually show that it is not necessarily true, right? So how do you do this? How do you show this? Well, one can use the well-known principle to show this. So what you do is that you represent the possible people as the vertices of a graph. When you take 6 vertices, and then let us say that if 2 people are friends, we connect them with a blue line, okay, and it's with colored blue. Now, by regional principle, a person who has 5 possible friends or acquaintances, right? They are saying like 5 people are others are there. Either he should know 3 people, or he should not. I mean, he doesn't know 3, right? So what we can say is that if you are going to say that whoever he knows I mark by blue line, and whoever he doesn't know by, let's say, a red line. Maybe red is not this one. For this, so this is red. So at least one of them must be of cardinality 3, right? 3 of them, right? Because totally there are 5. So by regional principle, we are going to just give 2 colors. One of them must be, right? One of the colors must have at least 3 elements. So once we find 3, then what do we do? Well, we check whether these two know each other. I mean, or not, right? If they don't know each other, then we put a red edge and we get a red triangle which says that there are 3 mutual strangers. Okay? So therefore we know that this cannot happen. So what must have is that this is blue edge, right? Similarly, if you look at these two, again, if I put a red edge, you get a red triangle. So therefore, this must be a blue edge. And what about these two? Again, if it is red, we get a red triangle. So we put a blue edge. So we get a blue triangle. So either you end up in a red triangle, which is three mutual changes, or a blue triangle, which is three mutual friends. Right? So this is unavoidable. But this is the idea. This idea we can carry over and then ask, what if I take a large enough complete graph, color all its edges with two colors, red and blue, right? What can you say? Can you guarantee that there will be at least a clip, a complete graph sitting inside, whose all edges are colored are just blue, or all edges are just red? Right? That is generalization, right? Instead of 3, we make it larger numbers. We can put it BT, right? So we want a set of T people, right, who are mutual friends or mutual enemies. Now, this, in fact, it's not immediately clear why we can always find a large enough number such that if you take a complete graph on that many, we will always be able to do this, right? But one can show it. In fact, if you are not coming across this, I encourage you to think about this, right? And show that this such a number exists, and you can always. So let me define it formally. The Ramsey number RT is given is the smallest or the minimum n that guarantees that to take a complete graph on 10 vertices, right? To take a n and then color all its edges with red or blue, then there is going to be a complete graph on t vertices, right? A subset of t vertices where all the edges in between, right? So the complete graph induced by this is either colored all with red colors or all with blue color, right? Which is called monochromatic. Only one color is there in the edges. So the Ramsey number is basically the smallest number that will guarantee that this will be the case. Now, as we saw in the case of when t is equal to 3, we had r of 3 was equal to 6, right? We had r of 3 is equal to 6. Well, because for 6, we showed that there is always either a red click or a blue click. And in the other thing, we could see of the complete graph on 5 vertices, there is no triangle of blue color or red, right? So, therefore, we know that R3 is 6. Now, the question is that what is R3 in general? Now, this turns out to be a very difficult question, right? In fact, if you want to find out R5 or R6, right, it's supposed to be almost impossible. Okay, we don't have the time to discuss the joke that Gregor made about this, but maybe we will see it some other time. Now, so what Andrews did is that he actually proved that this Ramsey number is exponential, right? It's it grows exponentially with t, right? So he said that he showed that the Ramsey number RT is strictly greater than 2 raised to 4 of t. Okay. So if t is 100, then 2 raised to 50 is a lower bound for the Ramsey. Right? Upper bound again, I encourage you to find an upper bound, which is something you can actually show using induction. Right? But you need some observations. So we are going to prove this lower bound using the probabilistic method. In fact, this is the first proof. Anyone that we know so far has some in using probability to show the existence of a combinatorial object. Okay. So the probability method, the first ever result is this one, showing the lower bound for rational numbers. That is by Ruled in 1947. So what he actually show is that if n to c, right? So this is the binomial coefficient n to c into 2 raised to 1 minus t t to 2 is less than 1, then the Ramsey number R of t is 50 greater than. Okay. So if n and t are just that, n to c into 2 raised to 1 minus t to 2 is less than 1, then the Ramsey number is at least n. Okay. And if you work with this inequality, one can actually derive this inequality. This is something that I will leave you to work with. But what we are going to do is prove this inequality. Now, what is the idea behind this? Well, if you want to use probability, we want to generate, a probability space, right? We want to basically define a random experiment, then associate the probabilities are there, and you want to basically, connect this with the probabilities of events, and then that's how we are. So we must define a random experiment. So what is a random experiment for us here? So we are going to do the following. We will take every edge of the complete graph on n vertices, right? Then toss a coin, right? Unbiased coin with probability half for the heads and tails, right? And then if it is heads, then I am going to color that with color blue, and if it is tails, I am going to color that edge with color red. Okay. So every edge uniformly and independently randomly picked, color either with red or blue with probability exactly half, right? Okay. So each edge with the red or blue uniformly and independently at random using I already said red one. Right, so this is our random experiment, right? Now once you have the random experiment, then you have to see how you make use of this or analyze probabilities of certain things. So what are we looking for? We are looking for complete graphs where all the edges have the same color, right? Either all red or all blue. Now suppose I give you a subset of vertices. Suppose I give you a subset of vertices, let's say S, whose cardinality is T, right? S is subset of let's say the n vertices. So take any real element subset, then I can ask what is the probability that all the edges, right, in this random experiment, right, all the edges of this particular set of vertices, right, the complete graph has become red. So what is the probability that all of them are red? Any suggestions? Well, every edge has probability 1/2 to become red, right? And independently of other, right? That's why we are using UIR, right? Uniformly and independently. So the given T vertex set, right, has how many edges in the complete graph? T choose 2. So we have T choose 2 edges. Each edge can independently be red, right? And since they are independent, we can multiply the probability, right? So we have 1/2 whole raised to T choose, right? That is the probability that all the edges are red. What is the probability that all of them are blue? We will be happy either all of them are red or all of them are blue, right? So for all blue also, same probability, right? So what is the probability that either all are red or all are blue, or it's monochromatic? Well, 2 times this, right? This plus this. So therefore, that is 2 times this, which is 2 raised to this thing minus 1, right? Because I am multiplying with 2, right? Okay. So this is for all this to be monochromatic, right? So this is monochromatic. So that is the probability for this thing to be monochromatic, right? Is that clear? So we define AS to be the event that the induced subgraph G of S is monochromatic, where the cardinality of S is equal to D. Then we know that the probability of AS is going to be 1 by 2 raised to n choose to minus 1, right? 1 by 2 whole raised to n choose to minus 1, right? What is happening here? Hopefully, yeah. Okay. So this is the probability for A, right? Is this correct? No, we had probability this for no, we have 1 by, so we are multiplying with 2, no? So what happens for 1 by 2 power? It will be minus 1. Right? 2 into 1 by 2 raised to n2, right? So this is 1 by 2 whole raised to n2 to minus 1, right? Or if you want to write it in another way, this is equal to 2 raised to 1 minus n2. Okay. So now we want to look at what is the probability that at least one of the T element subsets, right? At least one of the T cliques is monochromatic. Right? Because we are looking for one, right? We want to just show that there is some T clique. So we look at all possible subsets, all possible T element subsets, right? Which is AS, and then take the union of all, right? And we want to look at the probability for this, right? Probability that at least one of them, right? This is the at least one. So what is the probability? Here, the union bound of probability becomes very helpful, right? Union bound is the probability of a union is upper bounded by the sum of the individual probability, right? So therefore, we can write this as this is less than or equal to summation for all as a subset of n, right? What is that? Probability of x. But now what is this? This is probability of AS, we already know. For each AS, it is the same, right? So 2 raised to 1 minus n choose 2. And the summing of all possible T element subsets of them, right? So, how many T element subsets are there? N choose C T element subsets are there. For any of the subsets, probability of AS, the corresponding S, probability of AS is n choose C to 1, 2 raised to 1 minus n choose, right? Now, by assumption, right, by given fact, this is less than 1, right? This is strictly less than 1. This is given, right? Now, let us look at the probability that none of this, right, was monochromatic. So, what is the probability none of this is monochromatic? It is basically intersection of all subsets AS complement, right? AS does not have. And we want this to be true for every S, right? So we are taking the intersection, right? We want none of the AS to be happening, right? So we don't want anything to get to be monochromatic. So therefore, this is here intersection A is complement. And this we know is equal to 1 minus this guy, right? 1 minus probability of union A, right? Where union is over the elements subsets of N. Right? But since this is strictly less than 1, this difference is strictly greater than 0. Okay. So, as far as N2 into 2 raised to 1 minus d by 2 is less than 1, we will have some coloring, right, of the complete graph where none of the T elements subset is monochromatic. Right? So that is what we see, right? That we will be able to find that the probability that this happens is strictly positive. So that we will be able to find some coloring, like out of all possible colorings. At least one of the colorings must give that this none of the T elements of the are monochromatic. So that is the proof. Is that clear? Okay. So this is the first ever known proof in probabilistic method. So with this way I introduce this. Then we will use what is known as the linearity of expectation. Okay. So this is another tool from probability theory. So first we use the union form. Now we are going to use linearity of expectation. So what is linearity of expectation? That if you have a set of random variables, right, and you have some real numbers, let's say alpha 1 to alpha n, then the expectation of the summation over all these random variables scaled by alpha i's, right, is basically summation alpha into expectation of x. Right? This is basically this acts linearly. Right? So therefore, we have this. It's a very powerful result, very simple result, easy to prove also, but it is very helpful in proving many things. We are going to use this to prove some result in class A. So what are we going to look at is we are going to look at what is called the tournaments. Okay. So what is a tournament? Is basically a complete graph where all the edges have some orientation. Right? It's a directed graph where all the edges are directed and it's the base graph is complete. Okay. So the theorem says that if you have a tournament on n vertices, then first of all, okay, let me first show something else that if you take any arbitrary tournament, right? Tournament means that you have a complete graph. And then you have some orientation from the edges, right? So no matter how you are going to orient the edges, and if you orient all the edges, you will end up in what is called some tournament. Right? So this is a tournament on 5 vectors. Now first claim is that no matter what tournament you pick, you will be able to find some Hamiltonian path which is directed in this tournament, right? So this is something you can think about. How do you show that? There is always a Hamiltonian path in any directed tournament. Right? No matter how you are going to change the direction, you will still find some Hamiltonian path. Hamiltonian path means that a path with all the vertices right? Now, this is true that you can find one, right? But what about counting the number of Hamiltonian paths, right? So this theorem says that there is some tournament, right? Out of all possible tournament, where the number of Hamiltonian paths is very high, right? N factorial grows much faster than 2 raised to n. So therefore, this is a very large number. Exceptionally large number. So therefore, this is a very interesting result, right? And how do you show this? That is even more interesting. We are going to show that not just there is a tournament with this property. We are going to show that the expected number of Hamiltonian paths in a random tournament itself is large, right? Like this. Now, so this actually tells you the idea of the proof that if you show the expectation of something is, let's say, expectation of a random variable is, let's say, k. Real value random variable is k. Right? Expectation of a real value random variable is equal to k. Then, at least one of the instances, this random variable must take a value greater than or equal to k. Just like in the case of average, right? Because expectation is basically calculated by taking the value of the random variable multiplied by the probability, and probability is always less than or equal to 1, right? So therefore, if this happens, at least one instance, it should take the value greater than or equal to k, right? Similarly, less than or equal to k. We are going to use this idea in our proof. So now to show this, what we are going to do is that we take a complete graph and then generating a random experiment by picking each edge. Instead of coloring red or blue, we are going to give some orient, right? You take an edge A, B, you orient either A to B or from B to A. Okay. So this again we do with probability half. Okay. So orient edges of Kn uniformly and independently at random from, let's say just AB from AB from A to B, right? So A to B or B to A. The probability. For it, right? Okay, so we are going to do this. This is our random experiment, right? And then we are going to look at how we are going to count the Hamiltonian marks, right? So we are going to define a counting variable, and to count, what we are going to do is that we are going to take an arbitrary permutation of the vertices and check whether this defines a Hamiltonian bar. Right? So if it actually defines a Hamiltonian bar, we will set an indicator random variable. Like indicator random variable says that the event has happened or not. Okay? So it just indicates whether it has happened. So its values are either 1 or 2. Right? So if this particular permutation gives rise to a Hamiltonian bar, we will put the random variable to be 1. Okay? Corresponding to the corresponding to the permutation, right? So suppose we want to be an the vertices of the tournament, then the indicator random variable x sigma says that sigma is a permutation of 1 to n, right? Say that this permutation sigma of b1 to n is a directed form. Okay? So its value will be 1 if v sigma 1, v sigma 2, etc., v sigma n defines a directed path. What is the directed path here? Then the directions must be always going in the correct direction, right? All the edges are in the proper direction in this permutation, right? It's all going in the same direction. If that happens, then it will be 1, and otherwise it will be 0. Okay. So what is the probability of this happening? So what is the probability that this v sigma 1 to v sigma n defines this Hamiltonian directed path? So can somebody tell me what probability of x sigma? Well, just like we did in the previous case, you look at each edge. How many edges are there? Huh? How many edges are there? N minus 1 edges are there, right? Because it's a path. N minus x, there is a path. And these edges all must be in the same orientation. What is the probability for that happening? The first one, 1 by 2, right? Is going from v1 to v2, right? So v sigma 1 is 1 by 2. Second one is 1 by 2, etc. All the n are also 1 by 2. They are all independent, so 1 by 2 raised to n minus 1. Right? We can also see this by looking at what we are supposed to prove, right? 1 by 2 raised to n minus 1 is appearing there. Okay, so the probability of x sigma is 1 by 2 raised to n minus 1. Now, let me also define another random variable which counts, right? Using the indicator random variables, I can basically define another random variable x, which is summation of all the permutations x sigma, which basically now counts the. So given a random tournament, how many Hamiltonian paths are there? Right? Because each permutation you check whether it is a Hamiltonian path, it will count 1. If it is not, it will be adding 0. Right? So if you take the sum of all these random variables, it is going to give you exactly the expected number of, right? It's basically counting, right? Count the number, and expectation of x is what we are going to do, right? Okay, so probability of x sigma is equal to 1. What is this? This is precisely as we just found out, it is 1 by 2 raised to n minus. Now, for indicator random variable, the good thing is that the expectation and probability coincide, right? Because expectation of x sigma is probability that x sigma is equal to 1. And whenever it is not 1, it is 0, so it will not contribute anything, right? So therefore, this will be equal to, again, 1 by 2 raised to n minus. So by linearity of expectation, we can find the expectation of x, because expectation of x is equal to expectation of summation x sigma, which will be summation over all sigma expectation of x sigma, right? And this is summation over permutations, right? 1 by 2 raised to n minus. Now, how many permutations are there? N factorial. So this will be n factorial by 2 raised to n minus. Sorry. Okay. That is the expectation. So what is this expectation? It is the x is counting the Hamiltonian paths. So expectation of x is the expected number of Hamiltonian paths in a random. So the expectation is n factorial by 2 raised to n minus 1. And by our earlier observation, at least one of the tournaments must have this thing, right? One instance must satisfy. I mean, it may not be equal, it's at least that. So is that clear? That we now counted the Hamiltonian paths using probability and showed that there must exist such a tournament. Even though we don't know, it doesn't tell you how to count it, right? Other than going through all the things, it does not tell you anything, but it tells you that it must exist. Right? If you are really interested to find it, okay, you can do brute force now. But if you didn't know what it exists, brute force doesn't make sense, right? Okay. So now, yeah, I think I have written it down again. So yeah, we are going to the last part of my talk, and this is a very famous lemma, because using this lemma, I think around 1,000 papers at least must have been written by now, right? It's a result by it's a small lemma introduced by Roach, improving one of the results. But then Paul Reduce again, he noticed that this lemma is not, it's not a simple tool, it's very powerful. So what it does is the following: that in general, when we deal with probability, the problem is that when the events are not independent, we don't really know how to manipulate. Okay. So if there is dependency between the events, it is usually always done. But what this lemma says is that, okay, as far as the dependency can be classified by some local phenomenon, right? It's only in some local neighborhood of, right, the event. So you have many events happening, right? You have several events which are probably dependent, right? But we are saying that for each event you can find a small subset of events, and outside this small subset of events, the other events are usually independent of it, right? No matter what combination of other events you take, it's not going to affect the outcome of this event. If that is possible, then this lemma says something about the events not happening or things like that. So that's why it's very powerful, because it can deal with situations where the independence is not guaranteed. So we have a set of events, typically bad events. Right? We don't want this kind of events to happen. Right? Such that each event AI is mutually independent. So the name mutually is very important. Right? Mutually independent of a set of events says that we are not looking at any two events. Pairwise independence is weak, right? We are saying that any combination of the events also must be independent of this. So mutually independent of all except some subset of the event set, right? The A is the event set, then both of small subset, let's say DI, it can be dependent, but everything else is mutually independent. Now, if you can find a set of real numbers, such that is always following inequalities, right? Probability of each AI, right, is upcoded by this this scalar xi times product of all dependent events, right? One minus the associated, so each event is associated with the variable xi, right? So each event, we are looking at all these events which are in this dependent set, and then you look at the one minus of this associated variable, associated scalar. Okay? Now, if you can find a set of reals where this identity, this inequality holds, then Lowell's lemma guarantees that probability that none of these bad events happen, right? The intersection of all these events, that none of these events happen together, is strictly positive. Okay? That's what it says. Okay? Again, we can see now how we connect to our probability method because we are showing that positive probability for something. Okay? So to show that something like this, none of these bad events happen, right? Then our combinatorial structure exists. We can show that it must exist by showing the positive probability. So I'm going to introduce a problem that I worked on, but I introduced during my PhD time. We use the Lowell's local lemma to do it. So here it is that given a graph, we can look at several types of coloring, and we are looking at a type of edge coloring. Okay? So what is the kind of edge coloring that we are looking at? First of all, it must be proper that no two incident edges can get the same color. Right? If two edges are incident to a vertex, they must get different colors. Right? So no two edges can get the same color. So this is not allowed. Right? This is alright, but this is not allowed. Right? Then this is called proper coloring. Right? So we have proper coloring. Now we can put additional conditions on this edge coloring, right? We can say that okay, like you don't want any two edges at a distance less than 2 to get the same color, right? So it's even stronger than proper coloring. That's called the distance to coloring. Okay? But we are looking at we are looking at a particular vertex. Look at the set of colors used by the edges in the between. Okay? So you look at the set of colors. So this is supposed to be a different color. So you look at the set of all colors which is incident to the vertex. This I call as, let's say, CU. For the vertex U, CU is the list of colors appearing in the edges incident to that vertex. Right? Now, if you want to look at this coloring that we are saying, what we want is that for every edge you meet, the intersection of basically the adjacent vertices does not get more than 10 colors. That is what we want. So adjacent vertices does not get more than 10 colors in one, and if k is equal to 1, it implies that we are looking at what's called the strongest. So strongest coloring is, as I told you, distance to edge. So what we did is basically a generalization of strongest coloring and the proper coloring. So we will see So is it clear what is the kind of coloring we are looking at? We are going to color all the edges properly such that any two incident, any two adjacent vertices, the list of colors appearing there has at most k colors in common. Now here is some example, right? So you have a proper edge coloring where we have edges instead of a text does not get the same color, but this coloring is not, for example, two incident. Okay? That here you will see that if you look at this edge, blue edge, the neighbor, if you will these two edges will see three colors in common, right? So therefore, this one is not. So on the other hand, if you are looking at this one, right? This one X and this one, any pair of vertices we take, you will see that the number of common colors that happening is at most two, right? This is something you can verify. So therefore, this is called two intersection. Here is another coloring and for the edge UV, you will see that the intersection is the set 1 to 4. Therefore, it is a 3 intersection coloring in this. When 3 intersection definitely, we have to look at all possible case edges, but you will see that other edges definitely will not have more than this intersection. So therefore, this is a real. So in general, we have this k intersection coloring for a given case. Now, as I mentioned, when k is equal to 1, this is what is called a strong edge coloring, where any two edges which are even connected by an edge will not get the same color. Because if you have two edges of the same color connected by an edge, then the intersection here will be this 2 and this 2, right? So it will be 2. So this intersection is 1, right? We will not allow 2. This is not allowed. So that edges which are given at distance 1 cannot get the same color. So we need at least distance. On the other hand, when k is equal to delta, see, no two pair of vertices, no vertex has degree more than delta, right? So therefore, if k is equal to delta, we are not putting any restriction on the intersection. Because whatever is there is going to be allowed, right? So therefore, this is just proper coloring. So basically, as k changes from 1 to delta, we move from strong edge coloring to proper edge coloring. So now the question is that what happens when k ranges from 1 to maximum degree, right? Can you say something about the minimum number of colors that will be required to keep the same? Okay. So the k chromatic index is the minimum number of colors such that you have a k coloring of the edges of the graph, and we want to find a bound for this. So what we notice is that when k is equal to 1, this is actually linear. We know that proper delta plus 1 colors are sufficient by y is theorem. And when k is equal to delta, it has been shown that you need of delta square colors. Okay. So therefore, it goes from linear to quadratic, right? But what happens when k moves in between 1 and delta? So what we are actually able to show that this is actually growing something like delta square by k as k moves from 1 to delta. So this is our result. So they are saying that k of g grows with delta square by k, right? At least the maximum overall is that there exists graph where we require delta square by k, and we can always color with some constant delta square. Okay. So how much time I have? Okay. So we are going to use lowest local lemma for doing this. So how are you going to do this? So first of all, lower bound is something that I will give you as homework if you want to try it, but it's very easy. You just take a complete graph and try to round it. You will see that lower bound is immediate. But then what about the upper bound? Okay. So for the upper bound, we are going to again require a random experiment. So what is our random experiment in this case? It's going to be you pick some set of colors, let's say C, right? Then color each edge uniformly and independently at random with one of, let's say, a set of C colors. Okay? So we have C colors, and using one of the C colors, right? Uniformly, we pick one of the colors out of C, then give it to each edge, and go to the next edge and do the same thing independently. Now, what can happen, right? What are the events? So the idea of using Lewis lemma is that you will need to define a set of events such that if these events does not happen, then what we want happens, right? What we want is that we get a k intersection coloring, right? So we want to make sure that the k intersection coloring happens by making sure that this kind of bad events does not. So what are these type of events? So we define two types of events in this case. One is that for a pair of independent edges, the event EEF for fixed E and F, that the event that the edge E and edge F, which are incident, get the same color, right? If two edges which are incident get the same color, then that is bad for us, right? We want proper coloring. So therefore, we don't want such events happening. Okay? So this is a bad event. It's a type of bad event, right? For any pair of E and F, edges E and F which are incident, we have one event. So it's actually a collection of events, many events happen. Then you have a type 2 event that says that for a particular edge, you look at all the incident edges, right? Then there is a set, let's say, of colors here, and a set of edges here, and some set of edges here, which get the same color. Okay, but these both sets, have let's say k edges. In that case, what happens? Then we have k edges here and k edges here, and the one edge is in common, the edge in between. So we have k plus 1 edges in common with the same color, which will violate our k intersection condition, right? We want the intersection to be atmospheric. So therefore, this is also a bad event for us. Okay. So the type 2 event also is bad. But if we have, we show that the possibility of none of these two type events happening is positive, then we are good, right? Because the coloring will not have the same condition, and if it is proper, then we can. Okay, so let us try to do this. So first observation is that if two edges are adjacent, I will go a little fast because we have a little less time. Probability of EF type 1 event is 1 over C, right? Because the first edge can be given any color. The second one, if it gets the same color, then there is a problem. What is the probability that it gets the same color? Well, one of the C colors must be exactly equal to this one. Probability of choosing that is exactly 1 over C. So therefore it is 1 over C. Similarly, for each event of type 2, the probability of ES1S2 is precisely C choose K times K factorial whole square by C raised to 2. Now, how do I explain this? Well, C choose K is basically you choose any of the K colors. You pick the set of K colors that is going to happen, right? And then you are going to use that color on any of the some set of K edges here, and it must be also given to a set of K edges, right? But this now, this K edges, any K factorial permutations of this edges giving this color is okay, right? So there is K factorial possibility to rearrange them. Similarly, K factorial ways to rearrange. And this is presented in a number of ways. this can happen for any k set of edges, right? But then there are 2k edges here, right? K edges here, k edges here. Number of different coloring is 0 to 2k. 1 over c for each of them. So therefore it is this identity. But then we will use an approximation to make calculation simpler. Right? Get back to very Oh. What happened? Something must be there. Okay. So, here is the lemma. For each edge, the following holds true that at most 2 delta minus 2 equal to type 1 can depend on E, and at most 2 delta times delta minus 1 to k times delta minus 2 to k minus 1 equal to type 2 can depend on E. Okay. So, since we are lack of time, let me go a little fast. So, how do you show this? Well, for the first type of given, you will see that an edge can only intersect with the other edges in delta minus 1 here and delta minus 1 here, 2 delta minus 2 different ways. And for this other type of given, you need to have a central edge and then you need to choose some set of k edges here. How many ways to choose k edges here? Well, we have chosen already one edge E and another E star. Okay. Other than that, we have delta minus 2 here. And then you need k minus 1 more edges to make a set of k. And similarly, here you have delta minus 1 possibilities. And then out of this, you have to choose k, right? But now, how do you choose the central edge? You have 2 delta ways of doing that. It can be either this end or this end. So therefore, this will be the and 2 events only depend each other if they share some edge. Otherwise, we don't care. Right? The color is whatever happens doesn't matter. So we have all the necessary things to do this except for the constants. Okay? So we choose the constants by trial and error essentially. And if you put x equal to 2 over c and y is equal to k factorial 2 times k by 0 times k, then one can show that the corresponding inequality, the probability of ai, which is 1 over c, less than or equal to, right, 2 over c, the constant xi times 1 minus 2 over c whole raised to 2 times 2 delta. Then this is the number of edges and for each event we have almost 2 delta dependency, right? Similarly, for the other type of type 2 event, you have one event has 2k possible edges, right? 2k edges, and we have 2 into 2 delta raised to k by k factorial the k minus 1 factorial from our dependency boundary, right? So similarly for other inequality, and both one can work out and so that it follows from this if you assume delta is at least 6. But now delta is less than or equal to 5 follows directly by assuming that our constant is at least 22. And then that's it. So the result follows. Okay. So I will show. And if you want further details, references are here. Provolastic Method is book by Nobel and Spencer, and our paper on linear section as well. Okay, sorry I took 2 minutes extra with you. Any questions? Okay, there are no questions.
Thank you, Narayanan sir. The talk was very. Thank you, Narayanan sir. The talk was very informative. Any questions?
Okay.
Any questions?
Talks is over. Next talk 7 by Pradati Kahali, IISc Bangalore will be by 3 p.m. from 3 p.m. to 4 p.m. on big data in human genetics and genomics research. And later on by 4:10 to 5:55, we will have contributory paper presentation session 3. And at the same time, session 4 will also be happening. So those participants who have serial number CP18 to CP21 should log in with the other Zoom meeting ID given in the schedule. Those presentations having numbers C07 to C09, C14 to C17 shall continue with this Zoom meeting link itself. That will be from 4:10 only. The other parallel presentations by CP numbers also will be from 4:10 p.m. So the next session will be from 3 p.m. to 4 p.m. Thank you.